Many people have tackled the argument from complexity before, but they tackled it from a different perspective and they pointed out other problems with it. They pointed out how it's an argument from ignorance and how life and ordinary designed objects are not analogous. I would like to get more into how the argument from complexity is not simply an argument from ignorance, but deeper than that. Fundamentally, the argument is a form of equivocation, wherein two separate definitions are used to prove something, but it's treated as if both definitions are the same. Now, in technical fields, there's generally two different ways of looking at complexity. There's a physics definition of simply having a low entropy, and the perfect example here would be crystals. And the other definition is when you get to the differential equations, they tend to have high mathematical complexity, like nonlinearity or fractal emergent behavior. And a very good example here would be fluid dynamics of gases, which are compressible and oftentimes very complex because of that. Now, essentially, what you'll notice here is for these two examples, crystals have very low entropy, so they have complexity according to thermodynamics, but they have very, very much mathematical simplicity. And you'll notice that gases have very high entropy, so they're simple according to that definition, but according to the mathematical way of looking at things, their behavior can be very complex. Now, of course, that's not always the case. Sometimes you can get something with low entropy and high mathematical complexity. Quintessential example here would be life. So let's look at the features of things designed by man, the designed complexity of objects, such as computers and engines. What we'll notice is that the objects tend to be mostly or completely linear in their dynamics. The reason for this is because linear dynamics are much easier to solve for, and in fact, linear dynamics can always be solved. Solutions are guaranteed for linear dynamics, and so if they can keep things in a linear manner, they can always use mathematical techniques to solve them. So engineers try to keep things as linear as possible. Little to no fractal self-similarity. Sort of fractal emergence patterns tend not to appear in too many designed objects because that adds a whole new layer of complexity. And again, you'll actually notice that most of the things designed by man tend to deliberately avoid as much complexity as possible. They're as simple as they can possibly be while still serving their function. The next thing that you'll notice is they typically follow a one-part, one-function model. Typically, you'll have exactly one part serving exactly one function in the machine. You'll see this a lot in computers. You'll see it a lot, say, if you take apart an old mechanical watch. Each gear serves exactly one function. Another thing you'll notice is high degrees of synchronicity. You'll notice that each part is timed in a specific manner to work with other parts. This is almost always the case with most designed objects. And most designed objects are such that if things aren't synchronized, then they break apart. Good examples would be an engine, where all the pistons have to move in a specific timed manner, and if the timing belt on an engine slips, well, it'll be destroyed pretty quickly. And computers, which usually work on synchronous sequential logic, and rarely rely on asynchronous sequential logic, which often is very difficult to work with. And most computers, if something becomes asynchronous accidentally, well, the entire computer can crash. Now let's look at living things. In living things, there's high degrees of nonlinearity. Um, there's nature has no need to stay linear because nature really isn't interested in being understood because, well, nature doesn't really have a consciousness. Um, so being non-linear really isn't a problem. Um, you'll see huge amounts of fractal self-similarity. One of the most common types of fractal self-similarity you'll see in life is a branching tree pattern. You'll see it in trees, obviously. You'll also see it in bushes. You'll see it in the veins of, well, you'll see it in the veins of leaves of trees, but you'll also see it in the veins of, in blood vessels of various animals. You'll see it in the air passages of lungs, and you'll see it in the evolutionary tree of life itself. So there's a lot of fractal self-similarity, and that's only one type. There's other kinds of fractal self-similarity that occurs in nature, but the branching tree pattern is a very common one. The human body, as an example, is definitely not one part, one function, and very rarely is there a one part, one function model in nature. For example, let's look at the liver and the appendix. The liver serves somewhere around 500 separate functions for the human body. The appendix serves no function whatsoever, and you can live without it. The appendix used to serve a function back when humans were primarily herbivorous. It, I believe, aided in the digestion of cellulose, but it's really not doing anything now. Another example is the brain. The brain is not one part, one function. Certain types of thinking will require different parts of the brain working in parallel. Almost no thought can work with just one single isolated part of the brain. It almost always requires seemingly disparate and random parts of the brain to work. Thought is very difficult to map because of this. Consciousness is not the result of a single part of the brain. It's the result of many different parts of the brain that don't seem to be connected in any way. Another feature of life is that it's highly asynchronous, and again I turn to the brain. There's not a need for every part of the brain to be working on the same clock as you would have in a computer. Different parts of the brain can be doing things totally separate from other parts of the brain. You don't need to think about walking. You can think about something else while walking, and while your digestive system is working at the same time, and you're breathing at the same time, and your pupils are dilating and contracting at the same time, and you're blinking at the same time. All these things can be done at the same time with vastly different frequencies. Your breathing rate is only loosely connected to your heart rate. Your blinking rate is not connected at all. Your digestive rate is not connected. All these different things can be happening at exactly the same time on totally different clocks. You will not see this very often in designed objects because it adds a level of complexity that's simply not necessary. So, my point is that living things, while very complex, do not have the same kind of complexity. Designed complexity tends to be relatively simple. I say relatively, because it's still rather complex, but it tends to be relatively simple when it comes to mathematics. Designed objects tend to have very low entropy, so designed objects tend to be a little bit more like crystals. They have very low entropy, and they're not that complex. They're more complex than crystals, but they're still not incredibly complex when it comes to mathematics. Living complexity tends to be more like both the gases and the crystals at the same time, in that living systems tend to have very low entropy, but at the same time they have high mathematical complexity. This high mathematical complexity being something you would not expect from designed objects, but you could easily expect it from a certain type of natural system. Now, low entropy is very easy to explain in terms of energy transfer. Low entropy of crystals is very easy to explain in terms of how they're created. Low entropy of living systems is very easy to explain in terms of how they're created. The nonlinear dynamics is very easy to explain because, well, you don't expect nonlinear dynamics in things that are designed. So in other words, the type of complexity that you see in living systems is not even close to the kind of complexity and the kind of appearance that you would see in design systems. Just because they're both quote-unquote complex does not make them analogous. Complexity is, no pun intended, more complex than that. So, anyway, that's the end of the video, and I apologize. I currently have an infection.